Welcome to your first lecture on computer systems. And today we are going to take a look at the fundamentals of a computer system. So let's get right into it. What is a computer system about? Now, if you're anything like me, you are thinking about a traditional computer system that looks like this. And it has a screen, a keyboard, and some big tower unit there, and some peripheral devices. And but we as electrical and computer engineering students, we know better than this. And a computer system can be anything with a processor. And nowadays, that can extend from you know, any sort of device like a microwave, a refrigerator, a vehicle, and anything that has a processor. Really, it can be classified as a computer system. So let's take a look again at our course overview, and you'd see as a computer systems engineer, we would like to integrate the computer systems architecture, or the hardware, with some sort of optimization algorithm, as well as a software design approach. And any system which would allow us to interface and optimize with it and build it from scratch or modify it, that is a computer system. And so hence this entire course is dedicated to computer systems and how we can interact with it. So as a computer systems engineer, we would build systems containing hardware and software components, right? That's usually part of a larger system. And we would also like to develop new devices such as digital cameras, handheld computers, location-aware systems, and probably integrate several systems together as well, as you start seeing things like IoT devices, right? So you can start researching those types of components. Now, embedded computer systems is also becoming quite pervasive. We'll get an insight into embedded systems in the next semester for ECNG 2006, the Introduction to Microprocessors course. Computer systems engineers, they must make decisions regarding the way to design to have maximum impact and effect at a system level. Decisions have to be made about alternative approaches, trade-offs need to be addressed, and decisions on all these matters need to be justified on grounds of technical insight and judgment. Often computer engineer will be part of a multidisciplinary team that will have to react accordingly. So you would see that your role is quite important. And as a computer systems engineer, you need to have a very deep insight into the tools that you have to use, and you have to get a very good understanding of the architecture behind the components that you're using. So a computer system is defined as a collection of entities, which would be hardware, software, or liveware that are designed to receive, process, manage, and present information in a meaningful format. And this is kind of in the lines of what we did before in ECNG 1009, but now we have the hardware components to consider. So computer hardware are physical parts that are intangible parts of the computer, and they include input devices, output devices, the CPU, and storage devices. Computer software is also known as programs or applications, and can be classified into two types: system software and application software. Liveware, these are the users of the computer, and it's also known as orgware or humanware, and the user commands the computer system to execute instructions. So that's a big part of it, and we are, computer systems engineers who would like to integrate with the computer hardware as much as we can. Now, in order to do that, we must understand the architecture and the organization of the hardware device that we are dealing with. And there's a distinction between the architecture and the organization. The architecture is considered to be the attributes visible to the programmer. And these are the things that we know for sure that we can integrate with, right? And we must be familiar with things such as the instruction set, the number of bits to be used for representation, the input-output mechanisms, and the addressing techniques. Once we know that, hey, look, we can integrate with a processor, we need to understand how it works in terms of its architecture. Now, the architecture itself is pervasive in terms of the family of processors. So if you have a newer device as opposed to an older device, they may share similar architecture, which is unlike the organization, which is which focuses on how these features are implemented. So there may be difference in the way in which the hardware components are structured, the control signals, the interfaces, and the memory technology. So that has to do a lot with the organization and not really with the architecture. So as a computer systems engineer, you may be focused more on the architecture, and that will give us an avenue to interact with the device, right? And not really get involved with the computer organization unless you are developing that component yourself. Just as to give you an idea of what I'm talking about, you may be familiar with the Intel x86 family, right? They all share the same basic architecture. However, the organization may differ from generation to generation. But the architecture will give you some sense of compatibility, at least backwards. So what are the main functions of a computer? So we can cast our minds back to ECNG 1009, and we can remember that we built programs to process data, and that data came from somewhere, and more than likely it came from memory, right? And hence we had to store memory. So those are two main parts of it, and processing and storage. And of course, that data has to move around, right? And of course, there must be some sort of control for the processing, storage, and movement of data. So that is basically the main functioning parts of a computer. If you have a device that's controlling all of these things, then more than likely you have a computer. So what are the structural components of a computer? Now, since we made it this far already in our program, we should be able to tell what are the main parts of main components of a computer. And you are familiar with these terms already. They are the central processing unit, the main memory, and the input-output. And there's some sort of system interconnection that would tie all of these things together, which we will see in a short while. Now, we could dive a little bit deeper into the CPU, and we can see that the CPU is made up of registers, the arithmetic and logic unit, and control unit, and there's some sort of internal CPU interconnection. Now, we could dive a little bit deeper into the control unit, and we're going to get the sequence and logic, the control memory, and then there's some other control unit registers and decoders in there as well, but we're not going to dive into that deep into the processor for this course. Now, at this point in time, I would like you all to take a break, right? And you all can take a break and take a look at this link here, right? So it's a good opportunity for you to retrieve the slides for this session and find the slide and copy it and paste it into your browser and play this video, all right? So the name of the video is From the Pencil to the Keypad, and you can pause this video right now. Okay, welcome back. That was an excellent break, and I hope you learned a lot from that video, Pencil to the Keypad. And what I wanted to show you is that we have to take a historical look at, once we understand where we're coming from, where we came from, we can understand which direction we're heading. And you need to take a historical look at the evolution of computers. And I just want to give one note here, right? And which is war, right? Really does revolutionize technology, right? And that's a fact. As unfortunate as that is, it is a fact. And you would see that a lot of the technological advances came about around the during and around the end of World War II. And you could dig into the History Channel, and you could see that for yourself. And so there was a big battle between the Germans and the British and the Americans for technological advancement. So besides the fact of the war that was going on at the time, it was a technological race, because whoever won that, basically won the war. And so it so happened that at the end of the war, right, a lot of these advancements were released. And so around 1940s, the late 1940s, we had the ENIAC computer, which you can research, and then the first commercial computer was the UNIVAC, right? And of course, the Germans, they would make some counterclaims to that as well. So you all can take a look at your history and see what was the first machine. And so you can take a look at this link here as well, right, on the UNIVAC computer, and you'll see the importance that it played in the history of the world, right? So once we had our first commercial computer, obviously, as good engineers, we would like to come out with the new version very quickly that's a lot faster and a lot better than the previous version. And that also started another race, right, where people wanted to be better and faster and take up a lot less room. And so that led to another technological revolution, right? And that was the advent of transistors, right? So previously, the computers contain a lot of vacuum tubes. So you could look up what a vacuum tube was, and you could see the difference between a vacuum tube and a transistor is a big difference there. And it was obviously smaller. It was obviously cheaper to manufacture. It dissipated a lot less heat. It was a solid state device, no moving parts in there. And it was made from a very cheap material. And you all are familiar with this already because you passed through year one and you all had to do some sort of BJT project, right, for the end of year one, I think. And it was invented in 1947 at Bell Labs by William Shockley et al. And they all received Nobel Prize for this invention. And what I'd like you to do now is take another break, right? And watch this other video here, right? How transistors transformed electronics, right? So that is a very, very, very important part in history, right? And it's a big part in computer systems history, right? So it's a very exciting video, and I wish you would play it now. Right, so we'll take a break now and you can play it. Right, welcome back. That was an excellent video. And we had a look at transistors and how they transformed electronics. And you would have seen that it really led into the term microelectronics, where we wanted to get everything done in a smaller and smaller space, right? And we realized at this time that the computer was made up of gates and memory cells and how they were connected together. And I would implore you all to pay special attention to digital electronics, right? So I'd like you all to take a look at digital electronics with different eyes now, right? Where it's really the building blocks to developing a computer. And you would have done some digital electronics already, where you came up with your logic gates and so on. And if you wanted to do something a little bit different, you apply different control signals and you're going to get a different output, right? And that was really the start of a programming concept, okay? And that was the beginning or the revolution that happened with the advent of transistors. It made life a lot easier to do things like this, right? So the main goal here was to pack a lot of transistors into a very small space, right? And see how much we can do, right? So we had the first couple of generations there, right? A vacuum tube and then transistors, and then came like scale integration. So small scale integration where we were able to get 100 devices onto one chip, which was quite significant at that time. And then we scaled up to medium scale and then large scale by the 1970s, very large scale at the end of the 70s into the 80s. And then we have ultra large scale integration and so on, right? And what we realized is that we were increasing the amount of devices on a single chip, right? Well, more or less increasing the density, right? And so there were some theories that were floating around, and a very important one was the theory by Gordon Moore, right? So he's a co-founder of Intel, and he hypothesized that the number, well, he looked at the industry and said, okay, well, the number of transistors on chip will double every year, right? And a lot of people were speculating, oh no, we have really hit the top level of where we're at, and there's no way. But guess what? Because it's a race, and everyone is doing research on it, right? They found ways to improve the technology even more and more and more, right? So a lot of this was done. Research was done at IBM as well, and we have a Trinidadian guy across there who did work in the same particular area, right? And later on, I could maybe do an introduction to you all as well. So that was done. That was made. That hypothesis was made in the 1970s, right? And since then, right, you can say that it doubled up, right, every 18 months or so, right? So what could be interesting is, if we take a look at it, right, from then to 2005, it kind of held firm, right? But if you go further along in time, right, up to 2020, right, you could see that maybe it's holding firm there, but there are other things, other factors that are considered. And what would be a good question is does Moore's law hold true for today, right? And that is a very interesting conversation to have, right? So hopefully we will have that soon. All right. So a lot of things that happened, since the 1970s to present, right, that allowed us to come up to scratch with, keeping Moore's law. And there were several performance enhancements, and we would talk about these things in later lectures, right? And so some of it was pipelining onboard cache, right? So some of you all, you'll have to spec out some PCs and so on, and you know the amount of cache, and there's L1, L2, and L3 cache, right? Is there scope for an L4 cache? What does that mean? We'll talk about that in the next session. We are looking at things like branch prediction, data flow analysis, right? Speculative execution, trying to optimize the operating system. Looking at, but one of the main major problems, and you all are probably noticing that, from time to time, that yes, the processor speed is increasing, but the memory capacity is also increasing, and then we have to map the memory to the processor, right? And you'll see that the memory speed lags behind the processor speed, right? What's being done to mitigate that, right? So that's one of the issues there, right? And then we have the issues with multi-core, right? So yes, we could use multiple processors on a single chip now, right? But the challenge there is on the software and on the operating system. It must be able to support multiple cores, and there's a lot of complexity in there, right? And what sort of algorithms exist on that end? And this is where the first slide that I showed you earlier on, are we able to come up with the most optimal algorithms and interact with the hardware, right? To ensure that we are making the most out of that hardware, right? So, and then we could go into GPUs. You all are familiar with with GPUs because you all are speccing out your own machines and you're saying, oh yes, it must have the latest GPU, and it was really meant for video processing tasks. But then we realized that we can put a lot into the a lot of processing into the GPU as well. And we could farm out other tasks as well. And then there's general purpose GPUs as well too. So all of these things are come into play. Right. So the next thing that we want to focus on, right, would be the most fundamental computer system that we can take a look at, right? And that's the von Neumann machine. And how did it come about, and what are the steps that take place in the execution of an instruction, right? So we're going to look at that now, right? So of course we're talking a lot about hardware, right? And the whole purpose of hardware is to run software, right? And software is basically a bunch of programs, right? And so the whole computer system is based on this stored program concept, right? And it came about by a guy called John von Neumann, and in Princeton in, again, the 1940s to 50s, right? And so we realized that hardwired systems are inflexible. And again, this is where you can lend your your thinking now back to digital electronics, right? And coming up with your circuitry and so on, right? You know that hardwired systems are inflexible, right? And if we would like to make it a little more multi-purpose, right? Or general purpose, we need a different system, right? So general purpose hardware can do different tasks, right? Given the correct control signals, right? So it depends on the control signals that we give to the system, right? And instead of rewiring, right, and we just need to supply a new set of control signals, right? And so the program is a sequence of steps, and for each steps, there would be an arithmetic or logical operation done. And this is basically what is done within the processor. The processor is just going to execute some sort of instruction that you, the programmer, is telling it to do, right? Or the operating system, right? So it'll be done automatically, right? And for each operation, a different set of control signals is generated or needed, right? And we could really take a look at how FPGAs work, right? And I'm pretty sure you all know what is an FPGA. If you do not, well, this is a really good time to take a break, right? So take a break here, and I'd like you to take a look at this link. It's a really good break, and it's a really good link introducing you all to FPGAs. And it's about a half an hour long, right? But it's a really good idea to take a look at it. And I think Marcus, George would be very, very appreciative if you do, right? So go ahead and take a look at that. All right, so we're back from our break and we understand how FPGAs work, right? And since you have an idea of how that works, right, then it's quite easy to understand how this von Neumann architecture really operates. And it was first coined by John von Neumann, and it was the first stored programming concept computer that we had. And so the main functions here, right, it lends itself well to even a modern computer, right? So where we have the main memory, there's an arithmetic and logic unit, there's a control unit, and then there's some sort of input-output, right? So as I said before, well, he created this as part of the Institute for Advanced Studies, right, IAS, right? And it was completed in 1952. Right, and again, you can take a look, you can take a break, right, and take a look at this video just to get a better insight into that. Right, so this is the main components of the von Neumann machine, right? And it's really the building blocks of your CPU components, right? So the CPU components again is the control unit, arithmetical logic unit, and they make up the main parts of the CPU. Now, also associated with that would be data and instructions, right? And they would need to get in and out of the CPU via some sort of input-output mechanism, right? And then, of course, finally, right, the CPU itself would require some bit of temporary storage, right, of code and results and so on, right? And that's within the main memory as well, right? So all of these components made up the CPU, right? So the function of the control unit would be for each operation, a unique code is provided, right? And that is either to add, move, store, divide, whatever, right? And hardware segment accepts the code and issues some sort of control based on that particular operation, right? And once your processor can do these things, right? Well, then you have a computer basically, right? So the first machine, as I said, was the IAS machine. It looks something like this, and of course, it took up a lot of space, right? So this is, probably a significant portion of a floor of a building, and yeah, and this is what it looked like, and this was the logical structure of it. And you can see that is made up of the control unit, right? The ALU, the main memory, and there are some other things there. So wherever you see an R, right, that the R stands for register. So MBR, right, IBR, and so on, and IR. The R part stands for register, and register is a high-speed memory that's internal to the CPU. Okay, so whenever you're talking about registers, you're talking about the fastest unit of memory because it's stored in the processor, right? So as you can well expect, right, it's not going to take up much space, right? Because we're trying to be as efficient as possible, and the data there is usually temporary, right? So you want data to come in and out very quickly from registers, right? And then wherever you see buff or B, right, it's called a buffer, right? And so that's a temporary storage, right? And it's just used a buffer, as with any buffer, right? It's just used there to as a temporary storage to compensate for the difference in the timing of the occurrence of events, right? And then finally addressing, right? Well, you all should know what an address is, right? It's just the description of the location of an instruction, right? So that's that part of it, right? And then there are some other components that we need to take a look at, which is the PC, which is the program counter, right? So the program counter, as you can see here, let me use my pointer. Right, so this here is a program counter, PC, right? This contains the address of the next execution, the next instruction to be executed, right? So I'll say that again. The program counter, which is part of the control unit, contains the address of the next instruction to be executed, right? The instruction register, which is this guy here, all right, contains the 8-bit opcode instruction to be executed, right? So I'll explain how an instruction is decoded in a short while, right? Then you have the MAR, right? That's over here. That specifies the address in the memory of the word to be written or read into the MBR, right? And the MBR, right, which is this guy here, right, contains the word to be stored in memory or sent to the input-output unit, or is used to receive a word from memory or from the input-output unit, right? So this is really the one that interacts with the memory or the input-output unit, right? So once you have understood, these terms, right, then the operation of it would be quite easy. Now, you see there's another one here called AC, or that's the accumulator. Now, this is usually found in all processors, and programmers, they do have access to it, and it just stores the results of whatever operation, right? So it's a temporary store of operands and results in the ALU, right? So it's a very important register, right, called the accumulator, right? And of course, when you're doing micro-P next semester, by default, you would need to grab the information in the accumulator, right? And this is how it looks like. All right, great. All right, so so these are the definitions here, so you can take a look at it. And all right, so the next step is trying to understand the instruction cycle, right? So the instruction cycle involves two steps: fetching and executing, right? Is as obvious as that, right? So I did mention a little bit about these things here, right? These components, and we're going to talk about it in a little more detail, right? So in the fetch cycle, right, the program counter, as I mentioned before, right, holds the address of the next instruction to fetch. The processor fetches the instruction from memory location pointed by the program counter. In the meantime, we will increment the program counter unless told to do otherwise. The instruction is loaded into the instruction register, which will then decode it, right? And the processor interprets the instruction and performs the required action. All of that is the fetch cycle. So all of these things, occur within one clock cycle of the processor. That's pretty cool, right? The other clock cycle, right, or maybe a half a clock cycle, would be the execution, right? And as you can well imagine, this just sets up everything, right? And nothing else happens on, other than information is being retrieved and put into the registers. That's the fetch, right? We are fetching information, putting them into registers. The next part of it is the execute cycle. This is where we actually are doing the process, right? So the execute cycle would do several things, right? And there would be communication among a lot of the other peripheral type components, right? So for instance, we would need to do some processor memory transfer, right? So data transfer between the CPU and the main memory. Also, processor input-output, data transfer between the CPU and input-output. Some arithmetic and logic operations need to be done for data processing. And then controlling, right? The sequence of operation needs to be done as well, right? So all of these things and a combination of these things will be done in the execute cycle, right? So just to give you another example, right? We are dealing with instructions, and instructions are, the most basic element that a processor can understand, right? That's all it takes into a processor is are just instructions. The amount or the amount of instructions it can handle at a time, or the size of the instruction, and even the different type of instructions, all of these things would dictate what type of processor it is, right? But at the lowest level, right, instructions are just made up of two components, right? The operation code, or the opcode, and the address, right? Just two components. So once the instruction enters the CPU, it needs to decode that, right? And we'll see an example just now. And it's made up of two parts. The first part is the operation code. What is that? And the second part is the address. What is that? So the operation code is the actual instruction that a processor is capable of executing. Now, as I said before, your processor is limited by the different types of instructions that it can execute. Okay, and the number of instructions may define the type of processor. Okay, simple example, right? Our processor may be limited to perform the following instructions only, right? And the numbers there, 1 to 6, right? They represent the actual opcode designation of the processor. So let's say our processor can only do 6 things, right? And these things are load, store, minus, divide, add, and multiply. Okay, very basic, right? And that's all that we could do. In fact, you could probably program an FPGA to do that right now. And this is the main part of our processor. And our instruction would have part of it would be the opcode, and that's the first part of the instruction. And you would see a designation of 1 to 6 in our simple example, right? The address is the location in memory to access data to be processed, right? So we are going to do some operation on some data. Where is that data located? Well, that data is located via an address, okay? And so hence, an instruction register can receive an instruction, and the instruction is 1940. How do we interpret this, right? So how would the processor interpret this? So it knows that it's made up of the opcode and the address, and maybe the first part of it is the opcode, right? And if we go back, say, okay, 1, 2, 3, 4, 5, 6. 1 is load. Okay, great, right? So the first part of it is an opcode, and it's 1. And then 940, right? 940 is the address of the data that we'd like to access. So it's saying load whatever is in 940. So load anything stored at this address. And this is how instructions are decoded in a processor, right? And this is the most basic idea that we can have, okay? Now, I pulled this next example here from the Stallings, right? So you could go ahead and read that example as well, right? I'll give you the homework after, right? So this is the example here, right? And you can see that the program counter is storing the address of the next instruction to be executed. And so the program counter has the address. Let me use my pointer. Right. So the program counter has an address, and the address is 300. So we go to address 300, and we have an instruction in there, right? The instruction is 1940, and that is loaded into the instruction register. The instruction register takes in this instruction that needs to be decoded. And it just so happens that it's exactly the same example that we had in the previous slides. And it's 1940. And you can quickly tell that it says 1, load whatever is an address 940, right? So we go to 940 and we are going to load whatever data that we have here. And this data is 3, right? So the number 3. And I said that the accumulator stores the values, right? So what it's going to do in the next step, right, is actually load the 3 into the accumulator, and that's the result. And we can go on, right? So as I said before, right, the program counter, 300, right? This is the address, right? This is the instruction. And there we go, right? So the first step is we decipher the instruction, which is 1940, right? And we store it in the accumulator. Now, what happens simultaneously is that we are incrementing the program counter. The program counter will next increment from 300 to 301. So 301 is the address of the next instruction. So 301, and it's 5941, right? So 5941 is then sent to the instruction register, which is here, right? And then we need to decipher what this means, right? Of course, the first part is the opcode, 5, and 941 is the address. So 5 means add, right? And then 941 is the address. So what we need to add to whatever value is in the accumulator. So the accumulator is, basically a register that contains the value, the current value. So whatever value is in the accumulator, that's what we're going to do. So it says add whatever is in 941. So 941 has a value of 2. So add 2 to whatever's in the accumulator. So we're going to add 2 to whatever's in the accumulator, which is 3, and then we're going to store it as 5, right? So that's happening there, right? And then the next one, well, obviously, right? It's a loop, right? And we're going to go sequentially again, right? And the program counter will increment to 302, right? 302. And what's the instruction there? So it's 2941, and we put that in the instruction register. We decipher that, and 2 apparently is store, right? Whatever we have in the accumulator at the address 941. Right, 941, we used that before. It stored 2 before, but now we would like that to store the value in the accumulator, which is 5. So 2 is being replaced with 5. Okay, so this here is a simple example of how instructions are executed within a processor, right? So obviously, you know, this is the most basic method, right? And you have to be familiar with your own processor and understand how it would execute in for your purpose, right? For your own processor. Okay, so you may need to understand that by reading the spec sheets, right? In next semester for ECNG 2006, right? Just remember that, right? It's recorded here right now, right? So you could always go back to this. Okay, so let's go back, and we can remember that the structural view of a computer is like this, right? It's made up of the CPU, main memory, and the input output. And we all realize that there needs to be some sort of interconnection of all of these devices, right? And each one of these devices, right, they have a lot going on with with them, right? And you can tell that it's not just um, one line that's connecting each one of these things together, right? In fact, there are several things that's going on, right? So, for instance, with the memory, right? The memory here, right? What we saw from the last example is associated with memory would be an address and also data. So there's 2 separate lines, one for address and one for data, right? And what's coming out of memory would be actual data, right? So, and then there's probably some sort of sequencing or control going on that would allow us to know if it's in a reading mode or if it's in a writing mode, okay? And so these may be bits that would be set if it's a 1 or 0, right? Depending on the type of logic you're using, right? You'd know if it's in a reading mode or writing mode. And that would give you an indication to the CPU, right? If the memory unit is speaking or not, okay? Right, next we have the input-output module, right? And associated with that is also an address, right? And you're gonna have internal and external data, right? Internal data to the input-output device and external data as well. And then communicating from that would be internal and external data, right? And there's something different, right? Something new called an interrupt signal. So this is where an input-output module may request the CPU for some time, right? And it will issue an interrupt. And depending on the priority of that, right, the CPU may have to cease whatever it's doing, just to attend to whatever the input-output module would require. And then finally, we have the CPU, right? And again, there's the data side of it, right? That's coming in, right? Instructions also coming in. And then you also have your interrupt signals that could be from the input-output module, right? And then output from the CPU would be data, of course, addresses, and control signals, right? Because we need to control, all of the signals in our system as well, right? So this is the main parts of the computer, all of the computer modules, right? as I said, we have the memory connection, the input-output connection, and the CPU connection, right? And we went through each one of those already, right? So how is it all done, right? So how can we interconnect all of these very important modules that make up our computer system, right? Well, the answer is buses, right? Okay, not that type of bus. Get out of here. Right. Okay. Good. So buses, right? So buses are, a communication pathway connecting two or more devices, right? It's a shared transmission medium, right? And it's usually broadcast in nature, right? So once a device has control of a bus, right? It it only has one direction, and it takes full control of it, right? No one else is allowed on that channel, and that's it, right? So it's often grouped by function. So you could have a control, address, and data type buses. Okay, so it may be multiple type buses, and of course you may have different channels, right? So a number of channels in one bus as well, right? So for example, you may have a 32-bit bus. So this is the amount of data that a processor can process at a time, right? So if you have a wider bus than that, that's better, right? So you may hear of 8-bit, 16-bit, 32, 64 bits, and so on, right? And it's basically the number of channels within that bus structure. Okay, so as you can clearly imagine, that a CPU would have multiple lines coming in for controls, addressing, and data, right? And it would be connected to memory devices and input-output devices. And you could take, maybe there's a different type of structure, right? Or a hierarchy of bus structure that may exist, right? So you all could take a look at high performance buses, right? What is a mezzanine architecture, and so on, right? And if we need to connect other peripheral type devices, how does that integrate with our system bus? Okay, and then what's becoming more pervasive is high speed bus architecture, and so on. So you all could take a look at that. Now, one thing that we made mention to was the fact that our input output devices may interrupt us, right? The execution of the fetch execute cycle, right? So we spoke about the fetch execute cycle already, and maybe the input output device may like us to attend to something that's of higher priority, and it will interrupt our fetch execute cycle, and it will kind of bring everything to a halt there. And so this is what happens in the interrupt cycle, right? Is added to the instruction cycle, right? The processor would continuously check to see if there are any interrupts. If and it will be indicated by an interrupt signal. If no interruption occurs, well, then we just continue along with our fetch execute cycle, no problem. However, if there's an interrupt pending, what we need to do is suspend the execution of the current program, save that context, right? And then set the PC to start at the address of the interrupt handler routine, right? And let the interrupt handler process the interrupt, right? And then we can restore the context that we had before and continue the execution of the previous program, right? So there are different interrupts that occur at different levels of priorities, right? Of course, your processor will attend to the one that has the higher priority. Okay, so if one interrupt occurs, and then another one comes in with a higher priority like this, right? It would give the processor time to deal with the higher priority module. All right, so that's it there from the perspective of introducing you all to the fundamentals of a computer system, and we went through some really fundamental aspects of computer systems. And now it's your part now to, these are your assignments. So I'm going to put up this video now. You're going to go through it, and you're going to come to this part of the video that says, oh, what are we going to do next week, right? So for next week, we have two groups, right? And group 1 and group 2, right? And this is what they are going to provide for us, right? So you'll have 15 minutes, right, each, right? And the first group is going to demonstrate the evolution of Moore's law. So we spoke about Moore's law just now. And I would like you all to give some examples as well, right, of processors and devices and so on, and what is its applicability for today and for the future, right? So you have to make some bold statements about, in the future, what sort of devices that we're going to have. Of course, you're going to quote your references, right? And does Moore's law apply for today? Now, this is a really cool topic, and you're going to see a lot of debate online on this, right? Is Moore's law really truly Moore's law, right? In its truest sense, given all of these performance enhancements and stuff that's going on, right? Is it really a pure thing or not, right? So it would be really cool to see what group 1 comes up with, and they're going to share this information with us. So I'm really looking forward to what they have to say about Moore's law, and also to share that information with the rest of class, and hopefully you all can ask questions to group 1 on studying this Moore's law concept, right? And then the second group, they are going to take a look at the von Neumann architecture, but I'm going to put it to you now. There's an opposing architecture, right? It's called Harvard architecture. And guess what? You're going to be introduced to that in the second semester. What's the difference between the von Neumann and Harvard? And could you give us some example devices, right? So again, what you're going to do, you're going to recap this von Neumann architecture. You're going to put it in a much better way than I put it. And then you are going to now compare that to Harvard architecture. Well, what are the underlying differences between the two? Are devices now more centered around a von Neumann approach, or is it more on a Harvard approach, right? And we're looking at look at low powered devices, high power devices, and so on, right? And compare them and see. Maybe you may find some nice tables and stuff to share with us, right? So again, this would this would be very informative, and you could look into the PIC family, which is what we're going to be dealing with next semester, right? So it's basically some research and sharing the ideas basically for before we even start micro-P next semester, which is a very heavy course, and a lot of students have trouble with it. But if we are able to introduce students that right now, right, maybe you all will be better off for it. Okay. All right. So that's the assignments there. And in terms of readings, right, I would like you all to take a look at the Stallings, the first 3 chapters, right, all of it. And you would see that a lot of it would be what we discussed in this video anyway. And you all could take a look about on buses, and you can read up a little more on that. And what I would like you all to start doing is taking a look at intel.com and amd.com, right? And there's a big battle in the processor world between Intel and AMD. And those of you who have spec'd out computers recently, you all would be aware of this, right? And how what's the architecture, right, we are dealing with these processors, right? And some of the things we will talk about later on, right, and in other lectures, but it's really good to start looking at them and start looking at the processors and start getting a deeper a more technical understanding of of these processors. What would the AMD processors do that's different to the Intel that would make them a lot better, right? And the converse, right? Look at the specs of the Intel and and compare it to the specs of the AMD, right? Right, and you could take a look at this other link as well, right? On some internet fundamentals. The next session would be on the memory hierarchy, right? So again, we're going to have a lot of fun with that as well. Okay. All right. So that's it there from me, and I think that's it. Right. So I'll see you in class. All right. Bye.